Okay, hello everybody. I hope you can hear me because I think the video was not listening. Everybody hear me?
Yes.
Okay, thank you very much. So it's a place for me to give everybody the welcome to this art 2024. As you know, this is our 10th version, so we are very happy, very excited with this. And our first speaker in this occasion is Dr. Deborah Oliveros Branis. And as you know, I don't like to repeat the CV of Deborah. You can check this CV in our page, for example, or this is public information. So I prefer to talk about some histories of Deborah. Deborah and me made together our master's degree and PhD degree in the Math Institute. We have the same office as a student for many years. And we had many, many dreams when we were students. We dreams to be colegas, and we are colegas now, so it's very nice. We think maybe to be comadres. I don't explain comadres in Spanish, but everybody understands. Friends, more of friends. And we still be very good friends. We were co-editors of a journal for students. I am talking you about 32 years ago, so many time ago. We were co-organizer too to a special session in the National Conference of the Mexican Mathematical Society. This special session still be in every national conference. It's very funny because some years ago that I received invitation for this special session, and the organizer sent me explication, sent me all instruction about what is this session, etc. And then I say, sorry, but this is idea of Deborah Oliveros and myself. You don't need to explain me. This is very old work of Deborah and myself, etc., etc. So then I called Deborah my Coco for all of this co-author, co-organizer, comadres, colegas, etc. So this is my way to call Deborah. Unfortunately, the life take us parallel way. We are not now together, but I like to say that Deborah is one of the most important person during my studies, and she has very special place in my heart, and I am really very, very happy, and it's an honor for me that Deborah is in our card. So, Deborah, thank you very much, my Coco, to be here.
Thank you very much, Rita. I appreciate very much your kind words, and I feel very honored to be here. Thanks to all of you to be here. Please, I want to thank the organizer for giving me the opportunity to be here. Thank you so much, Rita. Please stop me if I'm boring you, or make me hurry up if I'm going too fast, slow me down. If I'm going the opposite, let me know. Please, I want interrupt me anytime. I'm happy to be interrupted, so don't worry. So let me just share my screen. Hopefully this will work. Okay. So I think I have to just. Okay. Do you see my slides now? Okay. So what I'll talk about is this strange, lots of words here. So don't pay attention much about this title. So let me just go a little bit over what I want to try to share with you. Let me just begin by saying that this is a work, pretty much an ongoing work. So there are lots of things that are unclear to me. In order to make things more easy for me to explain, I will say some minor lies. So don't, if I say something that is not quite 100% sure, the correctness is close enough. So it's just a matter of explaining things a bit better. So I will start by giving you some basic definitions. So these definitions are based on, the first basic definitions are about polytopes. So polytopes have been in our lives since very little. So perhaps all of you know these two-dimensional polytopes, which are polygons, right? I forgot to put here the triangle, but it's an important one. The square, the pentagon, the hexagon, don't need to be regular, are just examples of polygons. In dimension 3, the family of polyhedrons, which are 3 polytopes of dimension 3, I'm just going to concentrate in convex ones, are a wide variety of types. So here are some examples that I just stole from the internet. So here you can see an example of a 3-dimensional polytope or a polyhedron, and you can see that they could be quite complicated. So they are hard to understand. They have lots of properties. Some of them are interesting, and some of them, I mean, it's just some basic things. But generally speaking, all polytopes have a set of points, set of edges, set of 2 faces or faces of dimension 2, faces of dimension 3, and so on, etc. So for this conference or this talk, I'm just going to talk about dimension 2 and 3. Just because in dimension 1, there is not much to see, there is almost no interest in there. Dimension 2, almost everything is known, which is nice. In dimension 3, lots of things are known, but there are still lots of very interesting questions. And in dimension 4 and higher, almost nothing is known. So I'll concentrate in dimension 2 and 3. And sometimes I will mention some few things in dimension 4. So let me start with polygons. And I'm going to define what is the duality of a polygon. So I'm pretty sure most of you know what a duality is, but I'll recall you anyway. So take polygons, and for each one of your edges, take a vertex, like so. And I'm going to put an edge for 2 of these points, red points, if they have a vertex in common. So if I do this, then for the square, I'm going to get another square, for the pentagon, another pentagon, for the hexagon, another hexagon, and so on and so forth. So this means that all polytopes are self-dual. Why? Because when you do this operation of duality, you obtain again this same polygon, okay? Well, this means, now let me do one a bit further and just try to label the vertices. So if I have a square, so if I start with the square and then I do this dual operation, then this vertex A is going to be sent with this duality to another vertex. A, let's assume is going to be sent to the vertex A1, right? Well, if I do this operation once again, and I take the dual of the dual, so this is my dual now, and if I take now a set of points in each edge and do the same operation, I obtain another square. Okay, so what happens if what I'm doing then is the duality to the square? So what happens with my labelings? If this vertex was sent to this one, this vertex now is going to be sent to this one. So what this means is that the square of this duality is not the identity. Well, you may say, okay, what happens if instead of sending this vertex to this one, you send this vertex to this one? Does you get identity? Well, you don't. So what this means is that this square do not satisfy this property that to the square is the identity. What happens with the pentagon? Well, if you do the duality with pentagons, then if you send this vertex to the dual facet, then I'm going to label this as my dual facet. So this vertex is going to be the dual of this one. And if I do this to the square, so it makes the duality again, what I get is precisely the pentagon I started with the same labeling. So this means here that my dual is an involutive duality, okay? Well, it turns out that only odd polygons are involutive and self-dual. So I'm going to stick with polygons that are involutive and self-dual. That means I stay with the triangle, the pentagon, the heptagon, and so on, okay? Now, what happens in next dimension? So now we are in dimension 3, and if you take a cube, for example, I'm going to do the same operation. For every facet of my cube, I'm going to take a vertex, and I'm going to take an edge for 2 of these new vertices. If this edge, if these 2 vertices are joined by if these 2 facets are joined by the same edge. Now, clearly, if the dual of a cube is a octahedron, which is not the same, so then I'm going to say that this is not self-dual. Similarly, if I take the octahedron, the dual of the octahedron is the cube, so again, is not self-dual. But if I take the tetrahedron, the dual of the tetrahedron is tetrahedron. Therefore, a tetrahedron is self-dual. Okay, well, same thing happens if you take pyramids over n-gons, then these are self-duals. However, they are not, all of them are not involutive. Again, what I want is the existence of a labeling such that for every vertex, the dual one, so the one is sent to, satisfies that 2 to the square is equal to the identity. Well, just to give you an example, all pyramids over n-gons that have an odd number of vertices are self-dual polyhedrons that are involutive. If you take a pyramid over a square, so the pyramids, Egyptian pyramids are self-dual, but they are not involutive. But all the ones with base that is an even one, it's involutive. Here there are some other examples, but I should mention here right now that there is not really a way of knowing whether or not a self-dual polytope is involutive. So from the universe of all possible polytopes, we have the universe of the self-duals, and among this universe of self-duals, we don't know which ones are involutive polyhedrons. Okay, so I hope I'm doing fine so far. Please let me know if not. Okay. Now I want one further thing. I want metric embeddings of these involutive and self-dual polytopes. So what do I need? So imagine I start with my pentagon, and I know that for this vertex, this edge is precisely the dual face of this vertex. So this vertex is sent to this one over here. So a metric embedding for me is going to be a drawing of this graph such a way that the distance between A and all the vertices of the dual facets is 1. So the distance from here to here has to be 1. The distance from here to here has to be 1. So C, the dual facet of C is that one. So I want the distance from A and B to be 1 because B is A is in the facet dual to B, same to D, same to that. So what means a metric embedding is if you take a self-dual polytope, I want a drawing of this graph in such a way that the distance between this point and all the vertices of the dual facets are at distance 1. So this, for example, is a metrical embedding of the pentagon. Okay, observe that B and C could be closer, and this has not necessarily has to be regular, but what do I really need is that this graph, the purple graph that I just draw here, is what is called diametral graph. I want this that has length 1, okay? So in the dimension 3 case, for example, this is, I already told you that pyramids over pentagons are good examples of self-dual involutive polyhedra. So what would be a metrical embedding of that? Well, a metrical embedding of that, it's gonna be such that the distance from A and all these vertices here is at length, say 1, okay? Now, what's the dual facet of B? Well, it has to be a triangle. It turns out to be the triangle C, E, and E. So what I want is that the distance from B to A is 1, that I already have it, from B to C1, and from B to E1. So what I want is just that this diameter graph has all the edges of length 1. So this is a metrical embedding, okay? What happens in dimension 4, for example? Well, there are very few examples of self-dual 4-dimensional polytopes that are involutive, even fewer. And we don't, so far we have an infinite family of examples that of these animals that are self-dual, involutive, and metric ones. But in general, there is almost none example. So in dimension 4, almost nothing is known. But one thing, it's also an open question, is even in dimension 3, if I give you a self-dual graph that is involutive, can you draw it in a metric way? Could you embed this graph in a metric way? Well, Edgardo Roldán and some co-authors of him have a program on the internet that give examples of metrical embeddings of self-dual polytope up to 14 vertices, if I remember correctly. But in generally, this is an open question, which is by itself an interesting one. Okay, not long ago, last year, Jivan Lopez Campos, who's doing a PhD with us, and Jorge Ramirez Alfonsín, we proved that these graphs, that these diameter graphs, are 4 critical. What does that mean? It means that the chromatic number of this graph is 4, and furthermore, if you eliminate every vertex of this graph, the chromatic number of this graph is 3 for every vertex. So you can see right away here, if you eliminate the vertex A, what you obtain here is an odd cycle, right? In odd cycles, we know that the chromatic number is 3. So now you can right away try to follow what's going on. So what we prove is that every involutive self-dual polyhedron, if it's metric, then this diameter graph has no chromatic number 4. Well, we don't know if it's they are metric or not, but we know that the chromatic number, which regardless of it being metric or not, is critical, is 4 critical. Okay. You may ask at this point, why do we care about this? This is always an interesting question. What do you care? Okay, well, let me tell you 4 reasons of why do I care. I hope these 4 reasons convince you that these animals are interesting enough. Okay, let me begin with this shape. That is a shape that has been with us since we almost are born, like very little, which is the circle, right? What is the main property of the circle? Well, if you look at the dictionary, the circle is a set of points that are equidistant for a fixed point, which is the center, right? Okay. What else? Well, the circle has, as I already mentioned, is important in our lives since the very beginning of the history of humanity, and has this very interesting property that you can move very heavy things with cylinders from the circle that allow you to move heavy things. Another interesting property is that the circle has been used as a wheel, for example, has the center, and you can put a X over the center, and that will help you to make a nice wheel over there. Okay, but the main property of the circle has the property that the width is constant in every direction. So what do I mean by that? Take a figure, okay? And with this figure, take a pair, in some direction, take a pair of supporting lines of your figure. In this direction, this is going to be the width of your figure. If you do the same in every direction, then we're going to say that the figure has constant width. So if the width in every direction is the same, we say that the figure is constant width. Besides the circle, the simplest example is what's known the Reuleaux triangle. The definition of this figure is pretty nice and easy. You take a regular triangle of length of sides, say 1, and with center of each one of the vertex, take a circle with center at V and radius 1. With center at this vertex, a circle of radius A, and that's going to give you this part of here. Same with center at B, radius 1, take this part. With center at C and radius 1, take this part. Another way is to think about this is intersection of 3 spheres with center, each one with center at A, B, and C. This Reuleaux triangle was defined for the first time by Franz Reuleaux, who was an engineer. But this Reuleaux triangle has been known for centuries. There are several churches in Europe from the 15th century that uses this Reuleaux triangle as a decorative figure, for example. So let me define to you what the Reuleaux polygons are. So consider a metric, involutive, and self-dual polytope. So in here, for example, I have a drawing of an n-gon that is not regular, right? But all these edges have the same length. So then this same operation can be done. If you take any of these vertex and take piece of circle and you join for center of here, radius 1, the circle, and so on and so forth, what you obtain is a body of constant width. So these Reuleaux polygons are defined in general as intersection of spheres with center at the vertices of these metric, involutive, and self-dual polytopes. So the Reuleaux triangle is one of them. This is the pentagon Reuleaux. This is a nine-gon Reuleaux, etc. So these are all examples of bodies of constant width. There are some other examples, but so for the purpose of this talk, I'm just going to concentrate from the Reuleaux polygons. Okay. These objects has been used has lots of use things. For example, the movie projector used the Reuleaux tetrahedron, the Reuleaux triangle, sorry, to make the inventors of the brothers of the Lumiere make the movie projector to transform a motion, a round motion, into up and down motion to make this movie projector work. Another nice example that I like a lot is this rotary engine Wenkel, which is made by a Reuleaux triangle, and that instead of pistons have this rotary engine. Also, you can find in some places, for example, I took this picture from a sewer water in California that uses a Reuleaux triangle as a sewer water, also circular ones, and that's because square or other shapes will collapse and you can have the possibility of getting in. So that's why these things are used. Coins with these shapes are used in several countries, like Canada has these 11 guns. Bermuda coins have the Reuleaux triangles. Here there's a nice example of this triangle tower building in Berlin, which has been designed by Dorte Guttermann, which is a very famous architecture, who uses a Reuleaux triangle. If you go to a bar, you may find one of those. this is an interesting example of why it's important knowing that the circle is different from other Reuleaux triangle. You know, the circle is the only body of constant width that has a center. The other ones do not have a center. It turns out that the one of the is called this explosion was caused because there was a failure of O-ring seal, which was supposed to be rounded, perfectly rounded. So the engineers only measure some parts of it, but not they do not concentrate on having a center. So since it was not perfectly rounded, it was just a body of constant width, then this seal was not good enough to seal, and that's one of the reasons that caused this explosion. Okay, let me go one step further and go to bodies of constant width in dimension 3. So the definition is going to be the same for every direction. Take a pair of planes that are supporting your body. So if the width, this is going to be the width, the distance between these two flats. If this distance is the same in every direction, then the body is a body of constant width. Here are some examples of bodies of constant width that are bodies of revolution of two-dimensional figures of bodies of constant width that have symmetry, reflectional symmetry, like the Reuleaux triangle or the pentagon triangle. Give you some few examples there. But maybe you're tempted to say, well, can we define the Reuleaux tetrahedron? Yes, we can. Take a regular tetrahedron, so like this one, and suppose that this is, again, metrically, so the distance between this point and all the dual ones are a distance 1. And take the intersection of all these spheres with center at these points. So what you obtain is what's known as the regular tetrahedron. Well, unfortunately, this thing is not a body of constant width. The distance between this edge and this one is a bit larger than the width that is supposed to be. So if the length of your tetrahedron is 1, of the light sides of your tetrahedron is 1, this goes a little further, so it's a little larger, unfortunately. But in 1911, Meissner designed a way of get rid of this. And his design was pretty neat. So he just trimmed a little bit the excess on one of the sides. So when you take this tetrahedron, you can choose one side and you choose and leave it the side the way it is. And on the other side, you're going to trim the excess to get exactly what you want. And he did with some very interesting construction that I'm not going to talk about, but this is mainly the idea. So based on the Reuleaux tetrahedron, Meissner constructs these two different bodies of constant width. This is one of them, and this is the other one. Okay, so we still have some few examples of these bodies of constant width. Well, in 2017, so not long ago, Luis Montejano and Edgardo Roldan decided to play around and to see if they can generalize these Meissner constructions to other Reuleaux tetrahedrons. So again, remember that we were talking about these polytopes, which are self-dual, involutive, and metric. So take one of these. This is going to be like, say, the frame of these Reuleaux polyhedrons. And then take for the center of each one of these vertices of these polygons, take these spheres. So if I take this center at this center, then this is going to be a small sphere, which is you can see over here. With center at this point, this gives you the spheres here. If you center at this point, you give these pieces of sphere. So they are very strange, irregular, but what you obtain are what's known as Reuleaux polyhedrons. And again, these are not bodies of constant width. However, Luis and Edgardo had to find a way of trim the excess and find a nice family, infinite family of examples of bodies of constant width in dimension 3 with this thing. Okay, now let me tell you about, I'm done talking about bodies of constant width, although they are recurrent in me, so they will show up later on again. And let me tell you about another very interesting problem, which is known as the Varsony problem, or the frequent large distance problem. So this problem says the following. Suppose I give you endpoints. What's the maximum number of diameters that you can find over this set of endpoints? Well, this problem was proposed in 1934 by Hopf, and with found widths in dimension 2, he answered this question. So it says that if E is this maximum number where D is the dimension and V is the cardinality of the vertices, then this maximum number has to be N in dimension 2. And the question is, okay, well, how do I accommodate these vertices to achieve this maximality? Well, guess what? The way to accommodate these vertices to achieve this maximality is precisely by Reuleaux polyhedrons. So if you want to accommodate 5 points such that every pair of them, so if you achieve n diameters, then the best way to do it is if you accommodate in a pentagon, in a Reuleaux pentagon. If you have 4 of them, well, take a Reuleaux triangle and put the 4th point in any of the edges of your Reuleaux triangle, for example. So all the vertices look like that. Does that started to sound familiar? Okay. Well, in dimension 3, Grunbaum, Hepes, and Stratzigott prove that this maximum number of diameters is 2n minus 2. Well, let me just point out something interesting. I'm pretty sure most of you have heard about this equation. Vertices minus edges plus faces is equal to. This is the Euler formula, right? What happens if I plug these numbers for a self-dual polyhedron? Well, if a self-dual is self-dual, the number of vertices and the number of faces are going to be the same. So since n is my number of vertices, then this formula becomes n minus e plus n equal to, which if you isolate e, then e is 2n minus 2. Okay, so Hepes, Grunbaum, and Stratzigott prove that the maximum are these ones. But I just want to point out that just in case something is ringing down on the back. Okay. Well, later on in 2010, Kupitz, Martini, and Perles characterize all extremal configuration. And the way they do it is by doing what they call ball polytopes. So what is it a ball polytope? Well, it's a bunch of points on the space, and then intersection of spheres with center at these points and radio 1. So this is the ball polytope, right? And they prove that, well, oh, I erased that. Anyway, okay. They give a characterization of this extremal configuration. Sorry, for some reason, I removed the characterization, but okay, there is one characterization. Last year, Jivan and Jorge Ramirez Alfonsin, we come up with this nice theorem. Says that if you want to characterize how are the vertices of a strong critical Varsony, that solve the Varsony problem, well, it has to be strongly critical, what this means is that first one is that the vertices satisfy that there are 2n minus 2 vertices, the edges, sorry. The critical configuration is extrema, which means that the degree of every vertex is 3. So I want them to be polytopes. And strongly critical means that they don't have another configurations smaller inside. Well, we show that if we have points that satisfies the Varshoni problem, then this diameter graph of this object has to be 4 critical, and furthermore, this has to be Reuleaux polyhedron. So the things that solve the Varshoni problem have to be Reuleaux polyhedron, and furthermore, the diameter is 4 critical. Okay, I hope I'm doing good so far, and I have not lost you. I repeat again, if you have questions, please stop me. If I'm going too fast, also let me know. Okay. So I'll talk about another very nice problem, which is called the Borsuk partition problem. Okay. This is a problem that was defined by Karol Borsuk and says the following. Thus, every set in RD with finite diameter, so it's bounded, is the union of at most d+1 set of diameter less than diameter of 3? Let's play around with this a little bit to try to understand. So if I have a triangle, for example, I'm in dimension 2. So the question is, if I have smaller figures that are with smaller diameter than the triangle, are 3 enough to cover the whole triangle? Well, 3 are enough for the triangle, but let's go further. Let's think about something more difficult to understand. Let's think about the sphere, for example. If you take a circle and take a copy of the circle, but this says that has to have diameter less than diameter of the original one. So let's shrink it a little bit. How many copies of this orange one do I need to cover the blue one? Well, clearly I need 1 here, 1 here, and 1 here. So 3 of them are enough. Okay. So this is the question of Borsuk. In 1933, Borsuk himself proved that it's true in dimension 2. In 1947, Percal proved in dimension 3. In 1955, Eggleston proved independently, and Grunbaum and Hepes gave a different proof in 1957 of the same fact. So long time after that, in 1993, Hilkalai and Jenkan proved that it was false for dimension 1325. And they proved that for every n bigger 2014, there are counterexamples of this. So far, after that, there are some known counterexamples in dimension 64 and higher. So for those young, enthusiastic people around here that are interested, the problem is still open for dimensions between 4 and 63. Just to let you know. So we don't even know in dimension 4 what happens. Now, in dimension 2, as I already mentioned, in dimension 2, almost everything is known. Boltiansky showed that in dimension 2, he characterized all the sets that need exactly Borsuk number 3. So if A3 is the smallest natural number that is needed to cover that, so this is going to be called the Borsuk number. So we know that in dimension 2, the maximum number is 3. But there are some examples of objects that need less than 3. So say 2 or 1, etc. No? Well, not 1, but 2 of them. So what the work of Voltaire was to characterize the ones that needed exactly number 3 of them. And the way he did it is by showing that these animals are the ones that have a unique completion to a body of constant width. So imagine that you have a figure that is quite strange somewhere. And then this is of course not a body of constant width. So imagine that your figure has some holes in there or some things that are not quite of constant width. And take a body of constant width that completes that into a body of constant width. If that figure has a unique way of complete that body of that you started with, then that is going to have Borsuk number 3. Now, in dimension 3, unfortunately, that same argument does not work. Why? Because, I mean, the tetrahedron, obviously, the tetrahedron, you need 4 copies, because you need, if you are shrinking your tetrahedron for something smaller, you're going to need to cover each one of the vertices of your tetrahedron, and you have 4 of them. Then the tetrahedron for sure has this Borsuk number equal 4. But unfortunately, there are several bodies of constant width that complete the cube. I already give you the 2 Meissner ones. This is a family of bodies of constant width that Isaac Aurelio, Luis, and I constructed. If you are interested, they are called P-bodies, and they are completion of bodies of constant width. So this is not unique, the tetrahedron. So this is not going to work. In 2014, Butler and Jolt Lange published a characterization of all the Borsuk number finite sets up to 14 elements, and show that in general, finding a complete characterizations of families of bodies that have with finite numbers, that has a Borsuk number 4 looks hopeless. But something is not difficult to show is that the diameter graph of these bodies of constant width. So take your body and suppose that your body has A of S, this Borsuk number A of S equal 4, okay? And take the diameter of this graph. Well, the diameter of this graph is going to be, the diameter graph, is going to be take a vertex and take all the vertices that are at distance 1 of that vertex that you take. If you do the same to all possible, then you obtain a diameter graph. Well, it turns out that the chromatic number of this diameter graph gives you precisely the Borsuk number of this figure that you started with. So let me go back to this example. If this is your figure and you want to find out what is the Borsuk number of this figure, well, take the diameter graph, consider the chromatic number, and this is going to give you the Borsuk number. Well, as I already mentioned, we proved last year this very nice theorem that says that if you take points that satisfy the Varsony problem that are extremal, so they have no subsets that satisfy the Varsony problem, we show that the Borsuk number is 4 because we show the diameter graph has a chromatic number 4 and they are critical for all the ones that are Reuleaux polyhedron. So this gives a complete characterization of all the sets in dimension 3 that are finite and that has Borsuk number 4. Okay, this is, as I already mentioned, this is Jorge Ramirez Alfonsín, and this is Giovanni Lopez Campos. So I think I'm pretty much done. I just want to show you this piece of art that was painted by Man Ray in 1949. It turns out that these Meissner bodies were exposed on a mathematician gallery of things that had to do with mathematics. And Man Ray went to this exhibition. And when we saw these Meissner bodies, he got fascinated, and he painted a whole collection, not only of the main Meissner bodies, but the whole connection of mathematical things that he saw on that exhibition. And his exhibition is called Shakespearean Equations. And this is the painting he did inspired on Meissner bodies, which in his point of view, he resembles the skull of Yorick and the breast of Ophelia together. So that's it for me. Thank you very much.
Thank you very much, Deborah, for this very, very nice talks. Your co-author, Ramirez Alfonsín, was invited to CAR many years ago to sometimes talk with us too. So I don't know if we have any question or comments to Deborah right at the moment. And Julian is checking in Facebook because sometimes. But I didn't follow the transmission. Okay, Julian said no questions on YouTube by the moment.
I hope that I don't make you fall asleep.
No, not us. Not, of course not. That's really very interesting for me in particular. I remember when you were doing your PhD in these pentagonals and this carousel, you remember, I have very good memories of this. And I understand some things I didn't understand. Very interesting for me. I don't know if somebody have a question. I have a question about this. Nobody has nothing. I have a question about this problem that you put that is solving for the less equal to 3 and the greater equal to 64. It's open for between 4 and 63.
Yes.
And my question is about this proof. This proof bigger of 64 is theoretic proof or is with computational, or I don't know. I cannot imagine.
It is a very interesting construction done used for those of you that like matroids. So is used actually they use a hypercube and is using vertices with the coordinates 0, 1 coordinates, and they make a construction and this counterexample is a very interesting construction. I don't think I am able to replicate the construction, but it's pretty interesting, and it uses a matroid theory basically.
Okay, because it's very strange that just stopped in 63. Yes, because you say, okay, why 63? I don't know. And it's more interesting too that there is no proof for the equal 4. Yes?
No, we don't have a clue. I mean, we know that we have several examples of Reuleaux polyhedrons in dimension 4, which are metrical, embedding, and so on and so forth. We know examples of Meissner things in dimension 4, which are these p-bodies in dimension 4. But we don't even know if some other Reuleaux polyhedrons in dimension 4 could be used to construct bodies of constant width in dimension 4. So that's still a very difficult question. We don't even know what the chromatic number of these self-dual polytopes in dimension 4 is. I mean, we have examples, and some of them, all of them have so far the chromatic number 5, but we don't know if all of them do. I mean, we have no clue.
So thank you very much, because it's very interesting. We have many students in our in this moment that heard the conference, and I think that always it's good for them to know the difference sometimes between 2, 3, 3 to 4, and in this case, okay, we have a very big space between 4 and 63, but after 64, we know this is the magic of the mathematics.
Yes, that's
So,
right. Yes.
if nobody has more questions or comments,
Hannah has a question.
okay. Thank you.
Actually, not question, but remark. Deborah, very nice talk. First of all, thank you very much. But you mentioned about Borsuk's conjecture. I don't know whether you all know that Borsuk, Professor Borsuk, is a Polish mathematician, was Polish
Of course.
mathematician. And do you know game board Farmer? I think Polish students should know. It's exactly the name of the name of the game board, very famous, and Professor Borsuk is an author of this game. So if you don't know, please check. It's very nice game. I always with my son played, and even now when he's adult, we still come back to this game board, and from time to time we play.
What's the name of the board? What's the name of the game? Farmer?
Farmer.
Okay.
Yes.
I'll write it down.
Farmer. With animals, rabbits, and dog. You have cards, and you need to collect all of the animals, but sometimes dog can eat your rabbit, probably. The fox you can eat something different, but you can be protected with the dog. Bigger dog, there is a small dog. Very nice game board, authored by Professor Borsuk.
Nice.
And by the way, the borsuk in Polish language is a name of wild animal. I need to check. Borsuk. Somebody else from Poland knows the name, English name of borsuk? Borsuk. Badger.
Badger?
Badger. Also, mathematician connected with animals. Just remark.
I went once to this these places where they read your cards. This I forgot the name of this, where they read if you have some influence of some animals and blah blah. And the badger is supposed to be my animal. So nice. Thank you. Thanks for pointing that out. I'm gonna look for that game board.
And moreover, Deborah is a particular lover of animals.
The home.
The home. Okay. Gracias, Magda. Thank you. Thank you. Okay.
Okay.
So if we don't have any more questions, comments, we say again, thank you very much, Deborah, for your very nice talk. And we will continue in 3 minutes with our next speaker, Inas Ekin. I remember you that after our talk, we have the video talks of the rest of participants, etc., etc. So see you in 3 minutes. Thank you very much.
Thank you for the invitation. I'm very, very honored and appreciate the invitation.
Thank you.